All right, in this video, I'll continue the work we started in part 2, where we integrated part A and part B. So here we're going to start off with part C. So in part C, we've got the integral from 0 to power on 3 of sine squared theta cosine cubed theta. So it's just an integral of product of powers of sine and cosine. And as mentioned earlier, we've done a series of videos on these. The guideline is that if one of the powers is odd, we save one of those terms and then write everything else in terms of the other function. So here we can see that the power of cosine is odd. So what we are going to do is we are going to save a cosine. So we're going to have sine squared, cosine squared, cosine theta d theta. So we are going to save this term, and then we're going to have to rewrite this one in terms of sine. So if we do that, we know that cosine squared is 1 minus sine squared cosine theta. Okay, so then we're going to use the method of u substitution. So we're going to let u be equal to sine theta. Yeah, then du is going to be equal to cosine theta d theta. Then we have to deal with the limits now. So we are going to have the theta limits here, and then we're going to have the limits of u here. So when theta is equal to 0, u is sine 0, so sine 0 is 0. And then when theta is equal to pi on 3, okay, sine pi on 3 is root 3 over 2. So these are going to be our new limits now. So our I is now going to be integral from 0 to square root 3 on 2. Sine squared is u squared here, then 1 minus u squared there, 1 minus u squared. Then this bit is just du. If we clear the brackets, so this is simply going to be u squared minus u to the power 4. So it's just an integral of a polynomial. It's going to be u to the power 3 over 3 minus u to the power 5 over 5, evaluated between 0 and square root 3 on 2. Now, so then we plug in square root 3 on 2. So it's going to be 1/3 square root 3 on 2 cubed minus 1 over 5 square root 3 on 2 to the power 5. And then when u is 0, the contribution is just going to be 0. So from this lower limit term. Then this we can simplify. It's going to work out to, maybe let's just do a few steps. So what we can do here is we can factor out square root 3 on 2 to the power 3. So this term here. So if we have that one outside here, so square root 3 on 2 to the power 3, then inside the brackets we're going to have 1/3 minus 1 over 5. Then the power that's going to be left here is going to be power 2. So if that is to power 2, so it's going to be 3 over 4 here. Then this side here, root 3, square root 3 cubed is 3 root 3. 2 cubed is 8. Okay, then into this here is going to be 3 over 20. Then if we do everything accordingly, this gives us 11 root 3 over 160. So that is going to be that for part C. Then now going to part D. So in part D, we've got the integral from 1 to 2 of dx over x squared plus x. So the first issue here is which method are we going to use? Substitution is always the first point of contact. Here we see that if we differentiate this, we want to get 2x plus 1. We don't have anything like that there, so it means it won't be use substitution. But looking at this is a polynomial. We've got a polynomial there as well. So for polynomials, or polynomial of another polynomials, we've got partial fractions. So the next question becomes, is this factorable? And in this case, this is factorable. So then indeed we can go for partial fractions. However, since this is quadratic, we could also factorize this and then use a trigonometric substitution. But between those two, if you can use partial fractions, or that completing the square, then use trigonometric substitution. You can use either of these two. Typically, this one works out shorter or less challenging than this one here. So we're going to use partial fractions. So if we start with 1 over x squared plus x, if we factorize the denominator, going to have x into x plus 1. So we can write this in partial fractions. So yes, again, we've got a series of videos on partial fractions. We're going to post the link for you at the top here. So plus b over x plus 1. If we clear the fractions here, this thing is going to give us a into x plus 1 plus bx. And then there are two roots of this denominator. One of them is x equals to 0. If we plug in x equals to 0, it gives us a is 1. The other one is negative 1. If we plug in x is negative 1, it gives us b is negative 1. So that means our integral here is going to, we can write it as follows. So I is going to be the integral from 1 to 2 of 1 over x minus 1 over x plus 1. Okay. Then this simply integrates to ln x minus ln x plus 1 evaluated between 1 and 2. If we plug in x is 2, this is going to be ln 2. This is going to be ln 3. Then if we plug in x is 1, this is going to be ln 1 minus ln 2. Of course, ln 1 is 0. So this term is just going to be 0. And so if we simplify here, we're going to get 2 ln 2 minus ln 3. 2 ln 2 is ln 4, because it's ln 2 squared. And so we can leave this as ln 4 thirds as our final answer. Okay, so that was example number D. Now I'm going to go to example number E. in example number E, we have got the integral from 0 to pi on 2, 2x sine of x on 2. Here we have got a polynomial times a sine, and if you check through our videos or our video on tabular integration, this is a typical example of integrals where we can use tabular integration. We say those integrals which are of the form polynomial times either sine of ax, cosine of ax, or e to the ax, then these integrals we can use tabular integration. So that's what we're going to do here. So if we put 2x here, derivative of 2x is 2, derivative of 2 is 0. So again, if you check that video on tabular integration, then that's going to get you up to speed with what's happening here. For this one, we integrate. So integral of sine x on 2 is going to be negative 2 times cosine x on 2. Integral of this one is going to be negative 4 times sine x on 2. So this one matches to the second one, and the second one matches to the third one. So our I here is going to be, so I'm going to start with this one because it's plus 8 times sine x on 2, and then the first two terms work out to negative 4x cosine x on 2. Our limits are 0 to pi on 2. So if we plug in pi on 2 here, this is going to be 8 sine pi on 4 minus 4 times pi on 2 cosine pi on 4. So that's going to be the first term. Take away, and when x equals to 0, this is going to be 8 times sine 0 minus 4 times 0 times cosine 0. So that means that whole second term here is going to work out to 0. So, and then the first term works out to sine pi on 4 is 1 over root 2. Cosine pi on 4 is also 1 over root 2. So this is going to be 2 pi here over root 2. Then this simplifies to root 2 into 4 minus pi. All right, so that is going to be our example number E. So it's example number E. All right, so what we're going to propose now is that you have a go at the 5 other integrals here, definite integrals. So you can pause the video, and so if you just want to have a go at F, G, H, I, and J, okay, then when you continue the video, then you can compare with our answers. So if you just pause the video, work through these, and then you can compare with our answers. All right, we're now going to scroll down to our answers for the definite integrals F to J. By the way, if you have got any questions on any of the materials we're doing, or comments, or you'd like us to do a certain topic, please feel free to post your question or comment in the comment section below. And we hope these are useful to you. Please do not forget to just subscribe to our channel and like the video. Right, so for f, we have got a this is a polynomial divided by another polynomial. So we could think in terms of partial fractions. However, the problem we're going to have with this one is that the denominator is not factorable. So that means, but since these are quadratics, that pushes us to the other option, which is a trigonometric substitution. So because we've got a plus here, it's going to be a tangent, and so that's going to be our du. When x is 0, let's see how this goes. There's a typo here, so this should be x here. So x and dx here. So when x is 0, tangent is going to be 0 as well. Then when x is 3, tangent is going to be 1. Tangent is 1 when theta is ∅4, or 45 degrees in degrees. Alright, so the integral is going to be x squared is 9 tangent squared. Dx is 3 secant squared theta. That's going to be the denominator. If we factor out 9, tangent squared plus 1 is secant squared. And so this is going to cancel out. So we just have integral of tangent squared, which if we write in terms of secant, can simply be integrated to tangent minus theta. Then if we plug in the limits, that's going to be the value of the integral. Again, here we've got a rational function divided by another rational function, but this is not factorable. So we could use trigonometric substitution even for this one. But before we do that, we notice that if you differentiate this, you get a constant multiple of this. So u substitution is actually going to do it for us. But if you use trigonometric substitution, you can confirm that you'll find the same solution as we do here. So du is going to be 2x dx, so x dx, which is what we have here, it's going to be half du. And when x is 0, u is 9. When x is 3, u is going to be 9 plus 9. So the integral is going to look like this, which is simply integral, which is simply ln u, and then if we plug in the limits, it's going to give us ln square root 2. In h, again, we've got a polynomial of another polynomial. The denominator this time is a cubic. Question is, can we factorize this? Yes, we can. So we use partial fractions, because if it's a cubic, we can not use trigonometric substitution, because those ones, trigonometric substitution is strictly when the integral involves quadratic expressions. So since the second factor is an irreducible quadratic, the partial fraction is going to look like that. And then if we solve for a, b, and c, we find that a is 1, b is 1, and c is 0. So the integral is going to look like this. So this one we can integrate straight away. This we've actually already integrated here. That was exactly the same, so it's going to be exactly the same procedure. The only difference is the limits now, because it was 0 to 3, so now 1 to 3, so the lower limit is going to be 10. So, and then if we do this and plug in the numbers, we get ln of 9 divided by square root 5. And then for the next one, which is I, we've got a polynomial times a natural log. So we use integration by parts. So we let u be equal to ln 2x, it's going to be du. And then if dv is x squared dx, then v is x cubed. So here we x cubed over 3, we differentiate, here we integrate, and then we plug into the formula, which is uv minus integral of v du. Then this is what we're going to get for the second term, which works out to just integral of x squared. If we integrate that, we're going to have 1 over 3 times 1 over 3 is 1 over 9. And then from here, we plug in the limits. We use properties of logs and collect terms. It works out to that. For j, which is the last one, we've got powers of tangent and secant. So for this particular one, we see that if we save a secant tangent, then we can write everything else in terms of secant. Then we let u be equal to secant, so du is just going to be this term here. When theta is 0, secant 0 is 1. Theta is pound 4. Secant pound 4 is square root 2. So our new limits are going to be 1 to square root 2. We integrate this, we substitute, and that's going to be the final answer. All right, thank you for watching.